Calculating isotope abundance. So, by repeating the solution for nitrogen before, this is how we'd solve. If we were solving for the atomic mass, %1 times mass 1 plus %2 times mass 2. Okay. Add these together, get your average atomic mass. That's what we've done so far. However, we can use the same formula to calculate for 2% abundances. You might protest that we have 2 unknowns and only 1 equation, and by math we can't do that. Except there is a trick. We like tricks. Think about the sum of the percent abundances of the 2 isotopes. The sum of the percents add up to 100%. Now, since when we're doing calculations, we don't calculate with percents, we calculate with decimals, they need to add up to 1. The decimal abundances add up to 1. So the trick is to express both abundances using only one unknown. So for example, for nitrogen, if I was given the 2 masses, nitrogen 14, I'd plug that in the equation like I know. Nitrogen 15, plug that in the equation like I know. And the average atomic mass, plug that in. What I'm left with is I don't know the 2%. So I would always plug in x as my first unknown. But this time, instead of using a different letter for a different variable, the 2 unknowns are related. Whatever this is, the answer for this variable is 1 minus it. So we plug in x for the first unknown and 1 minus x for the second unknown percent. Okay, that's all you got to do. Plug in x for one, 1 minus x for the other. When we solve for x, that will give us the percent of 14 because we placed it with the 14. So if I go through and I do the math, I get 14x plus 15 minus 15x, distribute this 15 into the parentheses. Okay. I get 14.007 equals all this. Do basic algebra, combine like terms, so you end up with a negative x, subtract 15 from that side, you end up with a negative number, divide by the negative 1, 15 minus 14.007, and we end up with 0.993, x equals 0.993, which if we write that as a percent is 99.3%. So to find the percent of the other element, we can either say, well, 1 minus x, that's what we plugged in here, or just use logic. If it's 99.3%, the other percent must be 0.7%. The 2 add up to 100. So you solve for x. X is the percent of wherever you placed it, and then just subtract from 100 for the other percent. It's not difficult. So let's do this example. Copper is made of 2 isotopes. Copper 63. Plug that in like we know. Copper 65. Plug that in like we know. With an atomic weight of 63.546. Plug that in. For my first unknown, I put x. For my second unknown percent, I put 1 minus x. When you solve for x, that will give you your percent of copper 63. So go through and try and solve for x. I'm giving you a hint that one of them is going to be around 70%. So solve for x. Plug those answers in here, and I'll give you a couple minutes to do that before I come back and do it with you. So now I'll work it out with you. So all we're doing is solving for x. By solving for x, we're finding the percent of 63 because we put x in the spot for percent of 63. Wherever you put x, that's what you're solving for. So to solve for this, we distribute. We get 63x plus 65 minus 65x equals 63.546. 6. Combine like terms, and you get 63x minus 65x. That gives me negative 2x plus 65 equals 63.546. Now I want x by itself, so I need to get rid of this 65, so I subtract 65 from both sides. That gives me negative 2x equals a negative 1.454. I still want x by itself, so I need to divide both sides by a negative 2, and x equals 0.727. So what did this x mean? Well, that x was your percent of 63, because that's where we had our x in our equation. To write this as a percent, it's 72.7% copper 63. For copper 65, you can either go back and solve for your 1 minus x, or just think of it. The two must add up to 100. So you get 27.3%. Your homework is to complete these 11 practice problems. They go over all types of average atomic mass calculations. So you'll be solving for average atomic masses, percents, and masses.